Welcome back to the Deep Dive. This is where we really get into the weeds on cutting-edge research, distilling it for you, our technically minded listeners. Today we're looking at the frontier of diffusion models, specifically for inverse problems like image restoration.
That's right. And we're focusing on a pretty significant challenge in actually using these models for image restoration, or IR. Diffusion models, DMs, they're incredibly powerful, no doubt.
Yeah, the results can be amazing.
They can be, but there's this persistent issue, almost like an inherent contradiction around the perception distortion trade-off. You push for really sharp, perceptually high-quality images, and you often end up sacrificing fidelity. You get weird artifacts, maybe things that just don't match the original underlying structure.
Okay, right. So you want sharp, but you also want accurate. How do you get both?
Exactly. And that brings us to the framework we're unpacking today. It's called Kernel Density Steering, or KDS for short. The authors are proposing this as a novel way to handle things, specifically at inference time.
Inference time, so you don't need to retrain the base model.
Yeah. Precisely. That's the core pitch. It's designed as a plug-and-play enhancement. The goal is to promote outputs that are both robust and high fidelity. And it does this by basically enforcing a kind of structured internal agreement during the sampling process.
Interesting. Internal agreement. How does that work without external checks?
Well, that's what makes it elegant, really. It doesn't need any retraining, like you said. And critically, it doesn't rely on external verifiers, like CLIP score or other non-reference metrics to guide it.
Okay.
Instead, KDS tries to extract what the paper calls collective wisdom. It does this by looking at how a group and ensemble of different diffusion samples are clustering together at each step.
An ensemble. So you run the process multiple times in parallel.
That's the idea, yeah. And our mission today is really to dig into the mechanics of this. We need to understand the math. It relies heavily on mean shift theory to see how KDS calculates this wisdom.
Right.
We also need to see how they got around the big challenge of doing this in a really high-dimensional latent space. And then, of course, we need to look at the proof. Does it actually work? We'll check the empirical results on tough tasks like super resolution and image and painting.
Okay, let's start by maybe quickly recapping the basics of diffusion models for these kinds of inverse problems. Just to set the stage, they fundamentally operate through this dual process, right? Adding noise, then taking it away.
Exactly. You have the forward process first. This is where you gradually add Gaussian noise to your clean data sample. Let's call it $6. This happens over, say, $2 time steps governed by a stochastic differential equation and SDE. You end up with basically pure Gaussian noise, $6.
And then comes the magic part, the reverse process.
Right, the learned reverse process. This is where the engineering comes in. The goal is to iteratively refine that noisy state all the way back to a clean estimate. $7.
And that's where the neural network comes in.
Yes. The network, usually called epsilon theta, is trained specifically to predict the noise component, epsilon, that was added at each step. And the crucial part here is that this noise prediction is directly linked, it's proportional, to the score function of the noisy data distribution at that time, p epsilon theta.
The score function, that tells you the direction to move to increase the probability density.
Precisely. It guides the sample back towards the manifold, the space where real data lives.
Okay, so when we want to use this for image restoration, like fixing a blurry photo, we need to condition the output on that blurry input. How do people usually do that? I think there are two main ways.
Yeah, generally two main paths in the literature. The first one is probably the most direct. You train what are called conditional latent diffusion models, or LDMs.
So you bake the condition right into the training.
Exactly. You explicitly feed information, let's call it $2, derived from the low-quality input image dollar into the model epsilon theta.
Yeah.
So the network learns to estimate the conditional score function, locked in them in steplehup dollars.
That sounds effective.
It can be, definitely, but its success is really tied to the training data. If your model hasn't seen the specific kinds of complex, maybe mixed degradations you encounter in the real world, its ability to accurately estimate that true posterior distribution, PT, can become, well, a bit shaky, unstable.
Right. It might not generalize well to degradations it wasn't trained on.
Yeah.
What's the alternative approach then?
The second path is more about generalization. You use an unconditional LDM, one that's just trained on clean data, and then at inference time, you introduce guidance using Bayes' rule.
Okay, how does that work?
Well, the idea is you can approximate the gradient of the conditional distribution by combining the gradient of the unconditional score, which your model knows, with the gradient of the likelihood term.
The likelihood,
Yeah.
like probability of the degraded image given a potential clean version at a time t.
Exactly. But calculating that likelihood gradient, log, often requires you to know exactly how the image was degraded. You need to know the degradation operator, often denoted as $1, in the relationship Lass-Acker-Saxon. Ah, okay. So if you know it was just downscaled or had simple Gaussian noise added, $1.
Right. For those synthetic simplified degradations, $1 is known, and this approach works quite well. But think about real-world images. The noise isn't simple Gaussian. It's complex, maybe signal-dependent. The blur isn't a nice, clean kernel. You have compression artifacts maybe mixed in.
So in those cases, $1 is effectively unknown.
Pretty much, yeah.
Well-
Or it's just prohibitively complex to model accurately. And that's a major limitation for these inference-time guidance methods that rely on knowing $1.
Okay, I see. And this is precisely where KDS comes in, right? Because it's designed to work without needing to know $1.
Exactly. That's its key advantage in this context. It operates without knowing the degradation, but it still aims to achieve results driven by consensus, results that the paper shows can rival or even beat methods that do need $8.
Which brings us back full circle to that perception distortion trade-off. This isn't a new problem, is it? Oh, not at all. It's been a central challenge in image restoration research for, well, decades. Historically, if you optimized for something like mean squared error, the Tola 2 loss, you're basically approximating the minimum mean squared error, or MMSE, estimator.
And that gives you the lowest possible distortion, mathematically.
Correct. Lowest distortion. But the result is almost always smooth or blurry. You lose the fine details.
Okay, the opposite end is using perceptual losses, maybe JANs.
Right. If you use perceptual losses or JANs, you get sharp results, lots of high-frequency detail. That's the high perception side. But they often introduce their own problems. Weird artifacts, textures that aren't quite right, structural distortions, hallucinations, basically.
So where do standard diffusion models fit on this spectrum?
Diffusion models, just by sampling from the posterior distribution, tend to lean towards the high perception end. They can generate sharp details. But they can also latch onto these spurious high-density modes in the probability landscape, which correspond to those hallucinations or artifacts.
Ah, okay, so KDS is trying to fix that.
That's the hypothesis. KDS aims to guide the sampling process so that it only draws samples from the robust high-density modes, the ones where the ensemble particles agree. The idea is that these consensus structures correspond to the true underlying high-fidelity details, not the artifacts.
So it's trying to achieve both high quantitative accuracy, like PSNR, and high perceptual sharpness, like LPIPS, simultaneously.
That's the goal, yes, to find that sweet spot.
Okay, so if we compare KDS to other ways people have tried to improve diffusion sampling at inference time, especially methods that use ensembles or guidance, what makes KDS stand out? You mentioned it relies purely on internal consensus.
Exactly. If you look at existing strategies, especially for scaling things up, you see maybe two main camps. In text-to-image generation, T2I, people often use external verifiers for guidance.
Like using CLIP scores.
Right. Using the gradient of the CLIP score to push samples towards better alignment with the text prompt. But for image restoration, these kinds of metrics, which are often designed for classification or semantic similarity, they're not always great at spotting the subtle structural artifacts that actually violate image fidelity. They might think an artifact looks good semantically.
Okay, so external verifiers aren't ideal for IR. What's the other camp?
The other category involves methods like sequential Monte Carlo, or SMC. These try to reweight the sampling paths based on that likelihood term we discussed.
PAX PDS.
But that brings us back to needing the degradation operator $.
Exactly. SMC methods generally need accurate knowledge of all $. To calculate that likelihood, which, as we said, limits them in real-world IR scenarios. KDS neatly sidesteps both issues. No external verifier, no need for $. It relies entirely on the agreement it finds within its own group of samples, its own particle ensemble.
All right, let's dive into the core mechanism now. This is where the math meets the generation process. You said KDS is built on local mode seeking. That's the fundamental idea, yes. It draws directly from the principles of mean shift. Mean shift is a pretty powerful non-parametric technique used in clustering and data analysis.
What does it do exactly?
Essentially, it's a way to find the modes, the local peaks, or high-density regions of an underlying probability distribution without assuming the distribution has a specific form, like Gaussian.
How does it find these peaks?
It works by iteratively shifting data points. Each point looks at its neighbors within a certain radius, calculates a weighted mean of those neighbors, and then shifts itself towards that local mean. Points effectively climb uphill on the density surface towards the nearest peak.
Okay, interesting. So it's like points moving towards areas where there are more points nearby. How does that connect to guiding a diffusion model?
Here's the crucial mathematical link. It turns out that the mean shift vector, the direction and magnitude of that shift for $0.6, has a direct relationship to the gradient of the probability density function if that density is estimated using kernel density estimation, or KDE.
KDE. That's where you place a smooth kernel, like a Gaussian bump, over each data point and sum them up to get a smooth density estimate.
Exactly. So if you estimate the density using KDE with a kernel dollar, the mean shift vector is directly proportional to the gradient of the logarithm of that estimated density. So mean is proportional to a log density dollar. Okay, wait. That gradient tells you the direction of steepest ascent on the log density surface, right? The direction towards the nearest mode.
Precisely. So the mean shift vector is the direction towards the local mode, and that's the insight KDS uses. By adding a term proportional to this mean shift vector into the diffusion model's update equation, the SDE, KDS makes each particle do two things at once.
Two things.
First, it performs the standard diffusion update step, the denoising part guided by the model's learned score function. Second, it simultaneously performs a kind of collaborative gradient ascent, moving towards the local consensus region defined by where the other particles in the ensemble are clustering. So it's using the ensemble itself to figure out where the good regions are. How is this density actually estimated at each step for the whole ensemble z-tie?
Good question. At every time step t-tie, KDS takes the whole set of latent states from the ensemble, zt I1 n psi. Then for each particle zpt, it estimates the local density using KDE, just like we described. That's equation 1 in the paper.
Right, using a Gaussian kernel dollar centered on each particle z-tie, and there's a bandwidth parameter that controls the smoothness.
Exactly. The bandwidth doll is critical. We'll come back to that. But the key is, in regions where the particles are tightly clustered, meaning they sort of agree on the intermediate structure they're generating, the KDE estimate het t will be high. Those are the consensus modes KDS wants to reinforce.
And the gradient of the log of that estimated density is what gets added to the diffusion update. Can we look at equation 2, which shows how KDS plugs in?
Sure. Let's break down that equation. The first part is just the standard reverse SDE update for diffusion. dTt, right dTt. This has the drift term, VGIT, and the diffusion term involving DDT, and the score function nablog hat TCD, which is what the neural network epsilon theta estimates. This part does the main job of denoising and moving towards the target distribution based on the input condition $2.
Okay, that's the standard part. What about the KDS term?
The KDS contribution is the second piece added on, plus delta DTT, DTT2 nablog DT. Notice it also has the TTT2 scaling factor. That's important because it ensures the steering force from KDS is scaled appropriately relative to the noise level at time dollars, just like the main score term.
And deltat is like a strength parameter for the KDS guidance.
Exactly. Delta controls how strongly KDS influences the update, and the core is nablog T, which is that gradient pointing towards the local consensus mode we just calculated using KDE on the ensemble.
So what's the intuition here? What does adding this term actually do to the particles?
Think of it as a collaborative stabilizer or a filter. If one particle, say ZOT, starts drifting off towards a region that corresponds to an artifact or hallucination, maybe a spurious mode in the true density landscape, it's likely that the other particles in the ensemble won't be going there.
Right, because hopefully most of them are tracking the real structure.
Hopefully.
Yeah.
So the KDE estimate around that rogue particle will be low, and the gradient log T will point away from it, back towards where the other particles are clustered the region of higher consensus.
So it gets pulled back towards the group.
Exactly. It gets pulled back by the collective wisdom of the ensemble. This steering term effectively encourages all the independent samples to converge towards shared, robust solutions that are agreed upon by the majority, rather than diverging into individual, potentially artifact-ridden paths.
So it's like using the ensemble itself as an internal check for plausibility, instead of needing an external metric or needing to know the degradation.
That's a great way to put it. It's measuring structural plausibility against the consensus of its peers, all of which are trying to solve the same inverse problem conditioned on the same low-quality input, Eulers.
Okay, the mathematical idea of using mean shift based on KDE within the diffusion update makes sense, but now we hit a major practical hurdle.
Yeah.
The curse of dimensionality.
Yeah, this is a big one.
For a typical latent diffusion model, the latent space COE isn't small. The paper mentions maybe 64 spatial dimensions with 8 channels.
Right, so the total dimensionality dollars would be $64 times 64 times 8 equals 32,768 orderlers.
Trying to do kernel density estimation in over 32,000 dimensions? That sounds computationally infeasible, right? Wouldn't the variance of your density estimate be huge unless you had a massive number of particles?
Absolutely astronomical. You'd need potentially thousands, maybe tens of thousands of particles for the KDE to be meaningful in that high dimension. And running that many diffusion samples in parallel is just not practical.
So how did the authors get around this? This seems like it could have been a showstopper.
This is where I think the really critical engineering innovation comes in. They realized they didn't need to enforce consensus across the entire latent image representation Z-seal all at once. Instead, they could do it locally.
Locally, like in patches.
Exactly. KDS doesn't operate directly on the high-dimensional, noisy latent state Z-seal. Instead, it operates on smaller, extracted patches. And crucially, these patches are taken from the predicted clean latent state, which they call HAT.
Okay, hang on. Why use the predicted clean state TATs instead of the noisy state seed that's actually being updated?
That's a really important distinction for making the mean shift calculation stable and meaningful. Remember, HITA is a diffusion model's best guess at the final clean output Z-stat, given the current noisy state CETL-Z and the emit condition cyclers.
Right, it's like a denoised estimate at time t.
Exactly. So Watala lives much closer to the actual data manifold. The features in Haas are more representative of the final image structure. Trying to calculate mean shift consensus directly on the very noisy ZEEP, especially early in the process, would be difficult. The modes would be ambiguous, maybe unstable.
Ah, I see. So by working with Hasse, you're calculating consensus in a space where the structural details are actually emerging and becoming clearer.
Precisely. You're refining the consensus in the feature space where it matters most for the final image quality.
Okay, so they use patches from Haas. What kind of patches? The paper mentions a surprising choice for the patch size. $1 times a 1. That seems really small if you're thinking about image structures.
It does seem counterintuitive at first glance, but think about the structure of that latent map. $64 times 64 of 4 spatial locations. And at each location, you have an 8-dimensional feature vector, 8 channels.
Right.
So a $1 times 1 a patch at a specific spatial location, GJRIR, is simply that 8-dimensional feature vector, let's call it PJY. By applying KDE and mean shift independently at each of the 64 to ZEL times 64 equals 4096 6 spatial locations, they drastically reduce the dimensionality for the consensus calculation.
Oh, I see. Instead of 1 KDE and 32,768 dimensions, you're doing 4096 independent KDEs. But each one is only in 8 dimensions.
Exactly. And doing KDE robustly in DD dimensions is perfectly feasible even with a modest ensemble size, like N $2 or N $200 particles.
That's clever. Did they check if larger patches work better?
They did. The ablation studies, specifically Table 5 in the paper, confirmed this was the right move. When they tried using larger, say $3, 3 or $5 times 5 patches, even with overlap, the performance actually got worse. Because as soon as you use a larger patch, the dimensionality dollars for the KDE calculation increases significantly. $3, 3 times 8 equals 722. $5 times 5 times 8 equals 200. And with the limited number of particles nigh, like 10 or 20, the KDE estimate in those higher dimensions becomes unreliable again. The $1 times an O1 approach was the key to making it work robustly with a practical dollar.
Okay, that makes sense. So can we walk through the actual steps of this patchwise mechanism at each time step to us?
Sure. It's basically a 3-step process within each main diffusion step. First is patch extraction. For every particle dollar in your ensemble, you first get the predicted clean latent state hat from the main diffusion model. Then you extract all the non-overlapping $1 times a layon patches, covering all spatial locations either. So for any given location JA, you now have a little local ensemble of 8-dimensional feature vectors, one from each particle.
Okay, got the local ensembles of feature vectors. Step 2.
Step 2 is compute and apply patchwise steering. This is the core KDS calculation, but done locally. For each individual patch, Bij, from particle dollar at location J, you calculate its mean shift vector MPJ. This calculation uses only the local ensemble PJ at that location, typically with a Gaussian kernel dollars for the KDE.
So the mean shift vector MP-day points towards the consensus mode for just that 8-dimensional feature vector at that specific location, day, based on what all the lot of particles think it should be.
Precisely. Then you apply the steering update, just like in the main KDS idea, but patchwise. PESJ left arrow plus del J. This nudges the predicted feature vector towards the local consensus.
And this happens independently for all $9 particles in all 4096 locations.
That's right. It's a massive parallel refinement step. Every single pixel location's feature vector in the predicted clean latent space gets collaboratively adjusted by the ensemble.
Wow, okay, what's the final step then?
Step 3 is reconstruction. You take all these updated KDS refined patches for particle $1, and you simply reassemble them back into the full KDS refined clean latent prediction KDS-TI.
And this refined HTOC is what gets used by the main diffusion sampler, like DEDM or DPM solver++, to calculate the next noisy state, ZIT1.
Exactly. So KDS acts like an enhancement module that takes the standard prediction heading reg, refines it based on ensemble consensus using this patchwise mechanism, and feeds the improved version HTS back into the sampler for the next step. Algorithm 2 and 5 in the paper show this integration flow.
Okay, that loop continues until $2, but then you still have different final latent vectors. How do you pick the single best output image? You don't just average them, right? Because averaging would cause blurriness.
Right. Averaging the final outputs would take you back towards the MMSE estimate and lose the sharpness. So they use a specific final particle selection strategy described in equation 9.
What's the strategy?
Since KDS has already guided the whole ensemble towards a region of high consensus, the idea is to pick the particle that best represents that final consensus. They calculate the mean of the final ensemble for Aquawar semiads. Then they select the single final latent vector selector that is closest in terms of total 2 distance to that ensemble mean Nahaso.
So find the particle closest to the center of the final cluster. That makes sense as a robust choice.
Yeah, it acts as a final filter, ensuring the output is well aligned with the strongest agreement found during the whole process.
One last detail on the integration. That steering strength parameter, diluter. You mentioned it's time dependent. Why not just keep it constant?
They found it's important to modulate its strength based on where you are in the reverse diffusion process. The reason comes down to stability and exploration. Very early on, when teller's close to $, the latent states are mostly noise.
Right, the particles are likely far apart and haven't formed clear structures yet.
Exactly. If you try to force consensus too strongly using mean shift at this stage, when the signal-to-noise ratio is low, it could actually be counterproductive. It might cause instability or prematurely collapse the ensemble towards some noisy, low-quality structure before it's had a chance to explore properly.
Will they turn it off early on?
Essentially, yes. They set delta low if the normalized time $, is less than 0.3, meaning during the first 70% of the sampling steps, starting from $. This lets the standard diffusion process handle the initial phase of coarse denoising and exploration.
And then they turn it on.
Then, once the sampling enters the later, more critical refinement stages, when TT-GEC 0.33, the last 30% of steps, the latent states are much closer to the data manifold. Structural information is clearer, the particles are generally closer together, and the consensus mechanism becomes much more stable and effective. That's when they ramp up the steering strength, setting delta to a value like 0.3.
So apply the consensus pressure only when it's most likely to help refine details and reduce variance, not when it might mess up the initial search.
Exactly. It ensures the steering is applied strategically for maximum benefit.
Okay, let's shift gears now and look at the proof. Does this KDS mechanism actually work in practice? The author started with a simple conceptual test, right? A 2D toy example.
Yes, they use a 2D mixture of Gaussians or MOG setup. This is really useful because in 2D you can visualize the distribution of samples easily. And importantly, for this toy example, they could use the exact ground truth score function, not one estimated by a neural network.
Why is using the exact score helpful here?
It lets them completely isolate the effect of just the KDS consensus term. Any change in the sample distribution compared to standard sampling using the same exact score must be due to KDS itself.
Makes sense. What did the results show? It's figure 2 in the paper.
The results were quite striking. When they applied KDS on top of standard DDIM sampling, again, using the exact score, the distribution of the generated samples changed dramatically.
How so?
Standard DDIM produced samples that generally followed the true MOG distribution, but there was quite a bit of spread, a significant variance within each Gaussian mode. The KDS samples, however, were clustered much, much more tightly around the actual means of the true Gaussian components.
So much lower variance within the modes.
Significantly lower variance. It clearly demonstrated visually that KDS is actively performing mode seeking. It's pushing the samples to concentrate much more strongly around the high probability centers, the robust modes of the distribution.
Okay, that's a neat conceptual validation. But the real test is on actual images, complex tasks. Let's talk about the $4 times real-world super-resolution results. This is often a benchmark task.
It is, and it's challenging because real-world low-resolution images have unknown complex degradations. They tested KDS by integrating it with 3 different well-regarded diffusion model backbones for SR, LDMSR, DiffBIR, and CSR.
And they tested across multiple datasets.
Yes, standard ones like DIV2K, but also more challenging real-world datasets like RealSR and DrealSR. And crucially, they didn't just look at 1 or 2 metrics.
Right, you need to measure both fidelity and perception.
Exactly. So they tracked the standard distortion metrics, PSNR and SSIM, which measure closeness to the ground truth. But they also tracked a whole suite of perceptual and quality metrics, LPIPS, FID, NEMA, MANICA, CLIPIQ, and DISTs. These try to capture aspects more related to human perception of quality and realism.
And what was the main finding across all these models and datasets? This is tables 1 and 2.
The key finding, and it was remarkably consistent, was that KDS managed to substantially improve metrics in both categories simultaneously.
Both distortion and perception. That's unusual, isn't it?
It really is. Often when you tweak a method to improve PSNR, better fidelity, you see perceptual scores like LPIPS or FID get worse, less sharp, maybe smoother, or you improve perception, but the PSNR drops because you introduced artifacts.
But KDS improved both.
Yes. They consistently saw PSNR and SSIM go up, indicating better fidelity, and LPIPS and FID go down, lower is better for these, indicating better perceptual quality and realism. This suggests KDS might genuinely be helping to bridge that difficult perception distortion gap.
Can we look at an example? Maybe pick one backbone and dataset to see the scale of improvement.
Sure. Let's take the DiffBIR backbone, which is quite strong, and test it on the RealSR dataset that one's known for having pretty tough realistic degradations.
Yeah.
Using standard DDIM sampling as the baseline, DiffBIR achieved a PSNR of 23.21 and an LPIPS of 0.370.
Okay. And with KDS added, they used n-pentaroller particles here.
With KDS integrated, the PSNR jumped to 24.39. That's an increase of over 1.1 PSNR points, which is actually quite significant in SR research, especially on a challenging data set.
Wow, okay. And what happened to the perceptual score, LPIPS?
That's the crucial part. The LPIPS simultaneously dropped to 0.339. So you got a major boost in fidelity, over 1 PSNR point up, and a very noticeable improvement in perceptual quality. LPIPS down by 0.031 points. Getting both improvements together like that really highlights how effective that consensus guidance seems to be at stabilizing the generation of details that are both sharp and accurate.
That's compelling evidence for SR. What about image inpainting? That's another challenging task, maybe even more so because the model has to invent plausible content over a large missing area.
Right, inpainting is inherently multimodal. There could be many plausible ways to fill a hole, and the model needs to generate something structurally consistent and realistic. They tested KDS using an LDM inpainting model on the ImageNet dataset, specifically filling in a missing center box region. The results are in Table 3.
And the KDS helped there too.
It did, consistently again. For the DDIM baseline, the PSNR was around 21.03. Adding KDS boosted it to 21.35. Not a huge jump, but positive. More importantly, the LPIPS score improved, reducing from 0.140 down to 0.131.
And qualitatively, did the inpainted regions look better? Figure 5 shows some examples.
Yeah, the qualitative results are quite telling here. The standard DDIM sampling sometimes produced inpainted regions that looked a bit blurry at the edges, or had textures that didn't quite match the surroundings, or just looked slightly inconsistent. The KDS outputs, in contrast, generally showed much better fidelity in the filled region, smoother and more coherent transitions, and more plausible details overall.
Why would the consensus mechanism help so much with coherence?
Because if one particle starts generating a texture or structure in the missing region that doesn't really fit, it's likely the other particles won't agree with it. The KDS steering will then pull that particle back towards generating features that are consistent with what the rest of the ensemble is predicting based on the surrounding context. It enforces a shared, coherent vision for the inpainted area.
Makes sense. There's one more validation point I want to touch on. The interaction with classifier-free guidance, or CFG. CFG is almost standard practice now for boosting perceptual quality in diffusion models, right?
It is, yeah. CFG works by essentially amplifying the influence of the conditioning signal, like a text prompt, or in this case, the low-quality image, by extrapolating between the conditional and unconditional score estimates. You use a weight, often called dollars, to control how strong this amplification is.
But turning up dollars too high can sometimes cause problems, right? Like artifacts or oversaturation,
It pushes perception.
but can hurt fidelity or stability.
Exactly. High CFG weights can increase the risk of generating artifacts or unrealistic outputs, even as they make the image sharper or more strongly conditioned. So the question is, does KDS conflict with CFG, or can they work together?
What did the results show? Table 6 looks at this using diffbir again.
The results suggest they're actually highly complementary. They tested KDS across a range of CFG strengths using weights WDOE others 2, $4, and 60 sec. And at every CFG level, adding KDS provided a consistent boost to the fidelity metrics, PSNR, and SIM.
Even at high CFG weights where artifacts are more likely.
Yes. For instance, with a strong CFG weight of 26 sigors on the drill SR dataset, the baseline PSNR was 26.55. Adding KDS pushed that up significantly to 27.60, almost a full point improvement, while still presumably getting the perceptual benefits of the high CFG weight.
So KDS seems to enhance the underlying fidelity without interfering with the perceptual boost from CFG.
That seems to be the case. It suggests KDS is improving the fundamental robustness of the features being generated. By ensuring the core structure predicted by the ensemble is sound and agreed upon, it makes the whole system less prone to the fidelity degradation that can sometimes happen when you push CFG really hard. It's like KDS builds a more solid foundation, and then CFG can apply its perceptual enhancement more safely on top of that.
Okay, let's dig into the robustness aspect now. A key claim for KDS is that it doesn't just improve the average result, but makes the whole process more stable and reliable. How did they test this? A natural comparison seems to be against other ensemble-based methods, right?
Yes, the most direct comparison is against what are called best of n, or Bond, selection methods. These also use an ensemble of Knowler samples.
How do Bond methods work?
They're conceptually simpler. You just generate Knowler-independent samples using your standard diffusion sampler, like DDIM. Then, after all the samples are generated, you use some external non-reference image quality assessment metric the paper tested using LIQE and ClipIQA to score each of the Knowler samples. And you simply pick the one that gets the best score according to that metric.
So generate N, then pick the best one based on an external judge? How does that compare to KDS computationally?
That's an important point. In terms of the main computational cost, the time and memory needed to generate the Knowler diffusion samples, KDS and Bond are very similar. Both scale linearly with DOAO. KDS adds the patchwise KDE and mean shift calculation at each step, while Bond adds the cost of running the quality metric on the N final images. The paper suggests these overheads are roughly comparable for typical N, like 10.
Okay, so similar cost. How do they perform? This is tables 4 and 8.
The results here strongly favor KDS. Across various backbones, datasets, and metrics, KDS significantly outperformed the Bond selection methods.
Really? Why would that be? If Bond gets to pick the single best result out of N candidates using a quality metric, shouldn't that work well?
You'd think so, but the weakness lies in the reliability of those non-reference quality metrics when dealing with the kinds of outputs diffusion models can produce for inverse problems.
What kinds of outputs?
Well, standard diffusion sampling, especially when pushed for high perception, maybe with CFG, can generate samples that have subtle or sometimes not so subtle artifacts. Things like weird textures, inconsistent structures, maybe small hallucinations. The problem is non-reference metrics like LIQE or ClipIQA, which weren't necessarily trained for this specific failure mode, can get confused.
Confused how?
They might actually perceive some of these high-frequency artifacts as desirable sharpness or detail, and mistakenly give a high-quality score to a sample that actually has poor fidelity. Figure 8 in the paper shows examples where the image selected by Bond still contains noticeable artifacts.
So the metric itself isn't a perfect judge of true quality in this context.
Exactly. It can be misled. KDS, on the other hand, doesn't rely on a post hoc external judge. It builds the consensus during the sampling process. By constantly steering particles towards modes where they agree, it proactively filters out or suppresses those unstable trajectories that lead to artifacts.
So the idea is that KDS produces a whole ensemble where even the average particle is likely better than the single best particle chosen by Bond from an unguided ensemble.
That seems to be the case based on the results. For example, going back to diffBRR on real SR, KDS achieved that 24.39 PSNR. The bond method, using the LIQE metric, only reached 23.77 PSNR. That's a pretty substantial gap, confirming that the in-process steering towards consensus is more effective than just picking the best-looking one afterwards, especially when best-looking is judged by an imperfect metric.
Okay, that makes the robustness argument stronger. Now let's talk about the hyperparameters that control KDS itself. First, the number of particles, no baller. This directly impacts the computational cost, but presumably also the quality of the consensus estimate.
Right. Figure 6 explores the influence of knob dollars, and the results are pretty clear. Generally, increasing a dollar leads to better restoration quality.
Better in terms of both fidelity and perception.
Yes. As you increase non-dollars, you get more data points for the kernel density estimation at each patch location. This makes the estimate of the local density gradient, nobula log hap k, more accurate and robust. A more accurate gradient leads to better steering, which translates to improvements in both distortion metrics like PSNR sim, they go up, and perceptual metrics like LPI-PSFID, they go down.
Is the improvement linear with N? Does doubling N double the benefit?
Not quite. The gains are most significant when you go from a very small number of particles, say non-dollar prox 5 Rs, up to a moderate size like $1 prox $10 or $1.15. Beyond 1 NT dollars or so, the improvements start to plateau.
Why would they plateau?
Probably because at that point, the KDE estimate is already quite stable, and the performance is becoming limited by other factors, perhaps the inherent capacity of the underlying diffusion model itself, or the fundamental difficulty of the restoration task. So, while the computational cost keeps increasing linearly with no dollar, the performance benefit shows diminishing returns.
So there's a sweet spot.
Yeah, the ablation study suggests that for many practical purposes, using one $10 dollar, which they use for most main results, or maybe N15 Vive, hits a good balance between performance gain and computational cost.
Okay, the other critical hyperparameter is the kernel bandwidth for the KDE. This controls the smoothness of the density estimate. How did that affect the outcome?
The bandwidth the dollar plays a really crucial role in tuning that perception distortion balance. It essentially defines the radius or scale of interaction between particles when calculating the consensus.
What happens if the dollar is too small?
If Eller is very small, the KDE becomes very spiky. Each particle only interacts with its absolute nearest neighbors. This can make the density estimate noisy and might prevent the ensemble from agreeing on larger scale structures. You might get sharp results, but they could be unstable or lack coherence. It's like using a tiny bandwidth. In standard KDE, you get high variance in your estimate.
And if dollar is too large?
If dollar is excessively large, the KDE becomes oversmoothed. You're averaging over a very wide neighborhood. This tends to wash out fine details and forces the consensus towards the overall mean of the local ensemble.
Which, as we said, is like moving towards the MMSE estimate.
Exactly. So a very large dollar might actually improve your PSNR or SM because it's smoothing things out, but it will likely hurt your perceptual quality. Things will look blurrier, and metrics like LPIPS or FID will get worse.
So finding the right dollars is key to getting that simultaneous improvement in both fidelity and perception that they claimed.
Absolutely. The optimal value of dollars is critical for hitting that sweet spot. It needs to be large enough to provide stable consensus, but small enough to preserve important high-frequency details. The ablations in figures 6 and 7 really emphasize this dependency. They show that performance on different metrics can vary quite a bit with dollars, and the best dollars might even depend on the specific task or data set. So tuning dollars is an important practical step when applying KDS.
Okay, one final point on robustness. Did KDS help with the worst-case scenarios? Sometimes an ensemble method might improve the average, but you still get occasional really bad outliers.
That's a great question, and they looked at exactly this. Figure 4 shows scatter plots comparing the quality, PSNR and LPIPS, of individual samples from a standard DDIM ensemble versus those generated with KDS.
What did the plots show?
They showed that KDS didn't just shift the whole cluster of points towards better quality on average. It specifically seemed to improve the performance of the samples that were performing worst in the baseline DDIM ensemble, the ones with the lowest PSNR, or the highest worst LPIPS.
So it lifted the quality floor.
Exactly. It significantly reduced the number of outliers or really poor samples. This strongly suggests that the consensus mechanism is effective at preventing those catastrophic failure modes where a sample goes completely off track and generates severe artifacts. By constantly steering every particle towards a robust, agreed-upon structure, KDS makes the entire restoration process much more reliable. You're far less likely to get a single terrible result that ruins a batch. #tag outro.
All right, we've covered a lot of ground here, from the core idea of mean shift to patchwise implementation and extensive validation. So let's try to synthesize this. What does KDS really bring to the table for you, the listener, working with diffusion models for inverse problems? What are the key takeaways?
Well, I think we can boil it down to maybe four main contributions based on the paper. First, KDS itself is a novel approach. It's an ensemble-based inference-time guidance method that's built on a solid mathematical foundation, local mode seeking, using mean shift and KDE. That connection is quite elegant.
Okay, that's the core concept.
Second is the crucial engineering solution, using the patchwise mechanism operating on the predicted clean state house. This is what makes the KDE gradient calculation feasible by getting around the curse of dimensionality, allowing it to work with a practical number of particles like N10.
Right, the $1 times 1 patch trick. Third contribution.
Third, and this is perhaps the main selling point, is its demonstrated ability to enhance both fidelity and perception simultaneously. It does this by steering the samples towards these high consensus structures identified by the ensemble itself, pushing them towards solutions that are robust and agreed upon. And importantly, it achieves this without needing any model retraining, without relying on potentially flawed external metrics, and without needing to know the exact degradation process $.
Which makes it broadly applicable to real-world problems. And the fourth point.
Fourth is simply the strong empirical validation across multiple challenging tasks, real-world super resolution, and image and painting. The results consistently showed substantial improvements over strong baselines, not just in average metrics, but also in robustness, reducing artifacts, and improving the worst-case performance. It genuinely seems to provide a practical way to help resolve that persistent perception distortion tension.
So KDS looks like a very promising tool for making diffusion models more reliable and effective for image restoration tasks where both accuracy and visual quality matter.
It does seem quite powerful, but of course it's not entirely without trade-offs or considerations. As we discussed, there's the computational overhead. The cost scales linearly with the number of particles you choose to use. While $100 seems like a good sweet spot, it's still roughly 10 times the computation of running a single sample, even if fast samplers like DPM Solver++ are used for each particle.
Right, speed is still a factor.
Speed is a factor. And the other practical consideration is the need to tune that kernel bandwidth parameter $. We saw how critical $a is for balancing perception and distortion, and finding the optimal value might require some empirical work for specific applications or data sets.
Okay, so that sets up a really interesting final thought for you, the listener, to ponder. KDS demonstrates the power of using ensemble consensus for guidance, achieving impressive results but with a linear cost in other dollars and reliance on tuning nullers.
Right. So looking ahead, where should the research focus perhaps be prioritized? On one hand, should the effort go into mitigating that linear computational cost of ensemble methods like KDS, maybe exploring things like sparse ensembles, adaptive N, or clever ways to approximate the consensus gradient more cheaply?
Or on the other hand,
Or should the focus be more on the guidance mechanism itself? Specifically, developing more sophisticated, maybe adaptive strategies for selecting the bandwidth $1 automatically. Could we design methods where $1 adjusts dynamically based on the time step or the image content or the estimated complexity of the degradation, removing the need for manual tuning while potentially achieving even better results? How do we best balance computational efficiency with the power of adaptive, data-driven consensus?